Our first speaker for today's session, for session 3, will be Dr. Alicia Caruso. She's a spectral geologist at the Geological Survey of South Australia and joined the survey in 2021 following the completion of her PhD at the University of Adelaide that examined the use of airborne hyperspectral remote sensing for mineral exploration applications. So today Alicia is going to be presenting her work on mafic rock mineralogy as revealed by thermal infrared HyLogger analysis. Please join me in welcoming Alicia.
Thank you, Anna, and forgive my voice, everyone. I am at the back end of a vicious cold, but we should be good to power through. So first off, I'd like to acknowledge the traditional owners of the land where this work was conducted, the Gugutha people. And now we're going to start on to the thermal infrared. So why do we care about the thermal infrared for mafic rocks? It's really important to understand mafic rocks. These could host various mineral systems, nickel, PGE for example, and mafic minerals are not always easy to identify in drill core, as shown here. It's dark, as we're all aware, and it's not very visually separable. So the HyLogger here can help us identify common and also quite uncommon mafic minerals to clarify and help our mineral identification. So do you think these minerals are from the same lithology? The answer is no. They're quite different, really different silica values, but visually they do look very, very similar. So a brief slide on the HyLogger. I'm sure we're all pretty aware of how the HyLogger works. We're collecting visible near-infrared, shortwave infrared and thermal infrared reflectance data. This is ranging from 380 all the way up to 14,500 nanometres. We're collecting really high spatial and spectral resolution data. Lovely photo of the machine down at the Tonsley Woodall Laboratory here. And we're able to give you really high quality semi-quantitative mineralogical data across all of these wavelength ranges. So the thermal infrared in particular, it's not all about the shortwave infrared. We can get a huge amount of information on silicate minerals in the thermal infrared, and there is more to the HyLogger than white mica and chloride. Surprise, I know they're really valuable where they're used, but we have more to offer than just that. Not all of our mineral systems that we talk about here in South Australia have relevant minerals that are identifiable in the shortwave infrared, However, sometimes the thermal infrared can be a bit challenged to unmix these results really successfully when we're dealing with aspectral SWIR results. So this is when we're dealing with dark or mafic rocks. And shown here, this is a general summary plot you'll see if you use HyLogger data. And the top is showing the aspectral, which is all that purple stuff, which it's a lot of it. And you really can't tell anything from our shortwave infrared data. But the thermal data below, which is delineating a quartz unit, pyroxene unit, it's really showing you, bringing that to life, I guess, in a way. More information we can use. So a little bit about where the drill holes I'm going to talk about are based. They're within the Gawler Phase 2 region that's been mentioned earlier. It's covering the central western Gawler Craton. And in particular, I'm focusing on 2 drill holes from the Acacia East prospect, right up in there, about 50 k's east of Challenger. These are containing quite a lot of mafic material, and here are the thermal infrared summary plots. So the pinkish kind of units are very quartz rich, and the orange is some K-feldspar, whereas the red is plagioclase, and all of that purple is pyroxene. So we can see that it is really a very mafic couple of drill holes. So I'm going to talk about a few different indices today, and I'm going to start with our Felsic-Mafic index and relate this in with lithology. So this is a plot here demonstrating at the top we've got lithology, and at the bottom we've got our Group 1 thermal infrared mineralogical data. So here we can see that the Felsic-Mafic is really pulling this apart. So to explain, the longer wavelengths have less silica material within them, and then shorter wavelengths, so things at the bottom here that are here, are more quartz rich and have much shorter wavelengths, more in the 8,000, 9,000 kind of region. So when we're dealing with this kind of simplified lithology, we can see that the metamafic unit that is quite consistent throughout this drill hole has much longer wavelengths. There's also some separability with amphibole appearing kind of at the bottom of this particular drill hole. And with intermediate kind of material at the bottom, the very bottom of the drill hole, we can see there's really quite a lot of variation between pyroxenes and quartz, and we can see that differentiation based on the high resolution data we can get from the HyLogger. And in the second drill hole, again, similar kind of premise, nice and sharp boundaries, which is really great to see between the log and the mineralogical data. Again, the quartz unit, the metagranite is really pulled out very succinctly with the how it's quartz rich versus everything else within this drill hole that is primarily very mafic, including the interlayered metamafic at around 400 metres. We can see that there is that change between quartz material and also more mafic rich material. So one thing that's challenging, as I kind of touched on at the beginning, was that there can be a bit of a confusion with the thermal infrared with unmixing in the software, and it's really important, I think, to differentiate these subtle mineralogical changes in mafic units. And in this case, we're going to discuss orthopyroxene. It's really limited in these two particular drill holes, but we do know that there is orthopyroxene throughout these drill holes from petrological data. We have limited thermal infrared reference signatures for orthopyroxene. I think there's only a couple in our current library that our software uses to unmix all of this data. And it's known and has been discussed a little bit, and should be some future work to discuss and look into the different orientations of pyroxene and how you get different spectral signatures, and trying to pull all that data together so we can actually have a bigger reference library to pull from with that. So at the bottom here, this plot is showing the difference between augite and enstatite, so enstatite being orthopyroxene, augite clinopyroxene, and we can see that they're really similar, but they're also a little bit different, but the nuance is it's really quite small. So how else could we identify orthopyroxene in HyLogger data? So one potential way of doing this is using the visible near-infrared. So there's a new visible near-infrared spectral reference library created by CSIRO that is soon to be released. And this has got a huge new range of minerals across this spectral wavelength range. Previously, we've had 14 minerals in the Spectral Geologist software, but the new library's got 280 spectra. It's got a huge new range of minerals and elements, mainly focusing on rare earths, sulphides, and all mineralogy. And so this can help us integrate these new and different kind of signatures into our analysis, and this is beyond hematite and goethite, which is the main bag for the visible wavelength range. And this can help us confirm and understand kind of some mix-ups we might have in the shortwave infrared or in the thermal infrared. So applying this with the orthopyroxene kind of story, we know there's quite a large absorption feature at 930 nanometres, shown here in the grey, in the visible near-infrared. And this new library I mentioned has 3 different signatures within it. So from that, selected one and came up with 3 kind of approaches for this. So one was to identify a statistical match over a particular wavelength range, which is called AuxMatch, creating a scalar at the 930 nanometre absorption feature to try and assess the wavelength position. Maybe that has something to do with composition potentially. And then also generating a ratio scalar using the 550 nanometre and 930 nanometre kind of positions, kind of like what you would use in remote sensing with like a band ratio. But today we're going to talk about the first one, the AuxMatch. So this is a result of using the AuxMatch. So this was applied over that main 930 nanometre feature, and then assessing all the statistics from the Spectral Geologist software, I used a 2 standard deviation cutoff to examine the results that are only with the highest match. So in this case, warmer colours have a higher match, and the dark blue is that cutoff of 0.84 and below. And so we can see that at around 200 to 220 metres, we have a bit of a zone where there seems to be more of this present. And then also down 480 or so metres, we also have a little bit of a band. And there's a little bit smattered throughout, which is really exciting. And when we compare a couple of locations with thin section data, we can see there is orthopyroxene present in these thin sections, which is really positive. It gives us a bit of a boost for using this and potentially developing this a bit further. So ideally, we'll probably take some, hopefully take some more samples next year in a couple of locations where there's a lot more orthopyroxene and kind of validate and assess how well this kind of works. And so now on to the third and final index I'm going to talk about, the Sulphide Index. So our Sulphide Index is using a parameter collected by the HyLogger in every drill core, every tray that it scans. We're measuring primarily, it's the thermal infrared offset, and we're measuring high overall thermal infrared reflectance. So that can be sulphide-rich core, can be shiny things, and shiny things can also include tray ends and depth markers. So another big indication of good data in means good data out. That's quite key, I think, in all things, but especially here. This type of index is more drill hole dependent and so more relative rather than something absolute. There's no value that says yes, if it's above 0.1 it means bingo you have sulphides or not, and it's not going to tell you which sulphides you're dealing with. That's maybe something you could talk about with the new visible near-infrared spectral library. But here I'm demonstrating in one of these Acacia East drill holes the sulphide index applied and coloured by the lithology log, and the blue line on top is the company assay data for sulphur. So we can see that, there's a few little points I'm pointing out, which I'll come back to in a sec, but there's relatively nice correlation between where we have higher sulphide index results and higher sulphur assay results. There's something kind of funky going on here, and I'll come back and talk about that in a minute, but first we have some nice images. So from the core imagery, we can identify there are some disseminated sulphides throughout this drill hole, and we're seeing high sulphide index results. I think this is really positive, really encouraging, that even it's not just like a big wad of something, it's disseminated and we're still able to identify it with reasonable confidence. And coming back to that little sneaky bit, so if we zoom in a little bit more, we can see that there is some elevated sulphide index results, as shown with the core imagery as well. But also the thing to note with this assay data is it's primarily 4-metre composite assay data. So I think primarily we're dealing with a resolution challenge, just dealing with large versus really quite fine. So in our other drill hole, Acacia East 3, again, we see really strong, very nice correlations, especially obviously in a sulphide-rich unit, but also in the metagranite, we're seeing a higher sulphur assay result as well as high sulphide index results. And in this case, these look great. We're seeing some really lovely sulphide veining and more pervasive sulphides with really quite high values, and the sulphur as well as quite high. So this is really encouraging. I think this is really positive for using this index and applying it, and I think it's really easy to apply. It's already in your HyLogger data set. Come and ask me if you'd like to apply it. It's really easy. And yeah, that's the crux of the talk. But I think there's a need to validate your thermal infrared data. There can be some furphies, and I think that's the case with a lot of data just in general. There are things that you need to validate and assess. These are some really straightforward scalars that we can discuss and provide, and some of them are even built into TSG, which is a sneaky surprise. There's a new visible infrared library that's coming soon that will be really great, and I think really valuable to a lot of explorers with unmixing confusion and trying to understand sulphides a little bit more and rare earths. And we can identify sulphides in drill holes, which is really exciting. And there's more work hopefully coming on this next year in the Musgrave province. So thank you very much.